Good evening, guys. Is my voice is clear? Could you please reply? We'll start the session without wasting the time. And sorry for the delay. Yeah. So welcome to the session on power system. So in this session, I just collected a few questions from CL Wadhwa book. Okay. I'm going to give an explanation for those questions. And along with that, I'm going to cover some important discussion on every question. Okay. So I hope my voice is clear and you are able to see in the question also, right? That is the first question. Good evening, guys. Is my voice is clear? Could you please reply? We'll start the session without wasting the time. Okay, thank you, guys. Yeah, the first question, if you notice here, this is a question related to the topic called surge impedance. All right. So we know that the surge impedance is the impedance offered for surge currents. The surge impedance is generally we come across when we are doing the transient analysis. The first thing about the surge impedance is it is generally we come across the surge impedance, okay, only during what? Transient analysis, but not steady state analysis. Okay. Transient analysis means basically in power system we deal with the wave traveling. Why we are doing the wave traveling means to calculate the surge voltages which are entering into the substation equipments. So, and we are going to design the, the lightning arrestor and surge arrestor based on this transient analysis. Okay. Now, the basic formula for surge impedance is root over L by C. I hope you understand this. Surge impedance is root over L by C. Okay. And this is independent on the length of the line. For example, if length increases, inductance increase, capacitance will increase. Length, inductance is directly proportional to the length, capacitance also directly proportional to the length. So both factors will cancel together. That's why surge impedance is actually a real number. It's basically a real number. And a phase angle of surge impedance is what? 0. The phase angle of surge impedance is a 0. And ZS is what? Independent on the length of the line. Independent on length of the line. So for any length of the line, the surge impedance is always constant. Okay. So that's why, so always I say surge impedance is independent on the length. So the surge impedance for 50 miles long underground cable is 50 ohms. For 25 miles length it will be same. Okay. It will be always same. So yeah. Right. Most of you given the correct answer. It is what? Yeah. 50 ohms only. Okay. Yes. We'll move on to the next question. For load flow solution, the quantity is normally specified at a voltage control bus R. See, what is voltage control bus? See, any bus we can treat it as a voltage control bus. If you are able to control the reactive power at that bus. If the reactive power is in the control, you are able to inject the reactive power, you are able to consume the reactive power at that bus, then what? It is called voltage control bus. At voltage controlled bus, the magnitude of the voltage is predefined. You can able to maintain 1 per unit, 1.1 per unit, 1.05 per unit, 1.08 per unit, whatever the requirement you have, that you can able to maintain. So at voltage control bus, the voltage is always constant. Since the voltage is constant, and also what else can be specified? See, basically we have two types of buses, generator buses and what? The load buses. Generator buses and load buses. For these two buses, except one generator bus, in this one is what? Slack bus, remaining ng minus 1 is what? The original buses here. This one bus is what now? Slack bus. The remaining all are what? The normal generator buses we consider. So even you take it as load bus or generator bus, remaining all these ng minus 1 buses, P is specified. For all these load buses also P is specified. In fact, P and Q is specified. A load bus also treated as PV bus sometimes, even except one slack bus, remaining all generator buses also treated as what? The PV buses. But the condition is that you are in a position to control the reactive power. Yes, the generator excitation is adjusted. It can inject the reactive power, it can consume the reactive power at that bus. So it can able to maintain the voltage magnitude constant. Again, I am saying, if you want to control the voltage in power system at any particular bus or at any particular substation in power system, you need to have a control over reactive power at that bus. Simply speaking, at that bus, you are in a position to inject the reactive power, you are in a position to consume the reactive power depending on the system requirement. If you are able to do this, yes, you are a voltage controlled bus. At your bus, voltage magnitude is kept constant. So that's why it may be generator bus, it may be load bus, is treated as what? Voltage control bus. But the question is, are you able to inject the reactive power? Are you able to consume the reactive power? And smooth control is possible. These three conditions should satisfy. You should be able to inject the reactive power, you should be able to consume the reactive power, and smooth controlling of reactive power is possible. If all these three criteria are satisfied, yes, you are called as what? PV bus. There is nothing wrong. So at generator bus, P and V is what? Controllable, indirectly speaking. So V is controllable. So that's why. And load bus also having some reactive power controller, then that is also called what? A PV bus. So voltage control bus means what? Who are the specified variables under P and V? All the n-1 buses, P is specified. Only slack bus we need to calculate P. And then V is specified or not, that depends on what? Whether in a position to control the reactive power or not. Now somebody asked the question like, is always the generator bus is called PV bus? The answer is no, because every generator having reactive power limits. If the generator bus is satisfying the reactive power limits, that means the reactive power requirement at the generator bus is within the limits, then it is called what? PV bus. Otherwise it is treated as what? PQ bus. Now tell me, a load bus always called PV bus? Strictly speaking, load bus generally called PQ bus, but a special case it is treated as PV bus whenever it has a reactive power controller external to the, at that load bus, an external element, that is reactive power controller, is connected. The best example for reactive power controller is SVC, static wear compensator, STATCOM, synchronous phase modifiers. These are the best examples for reactive power controllers. Okay, I hope this is clear for you. So finally, P and V are known values here. Clear? A load bus with what? Reactive power controller. Better to write like this. Is called PV bus. If nothing is mentioned, what is generator bus means? What is generator bus means? I will say PV bus. What is load bus means? Nothing mentioned. Whether it is having reactive power controller or reactive power is within the limits or not. Not mentioned means what? Load bus always PQ bus, generator bus always what? PV bus, except one generator bus. That generator bus is what? Treated as slack bus. Okay, I hope you understand this. This is a commonly asking questions. Okay, clear? Next, more relay is normally used for the protection of. See, generally for short line protection, short transmission line protection. Okay, just hold on. In the question also, right? I'm just checking whether this red pen is okay or not. Yeah. So short transmission line, we always use reactance relay. Medium transmission line, we always use impedance relay. long transmission line, yes, we use more relay. But whatever I said here, this is valid for what? Phase fault protection. This is valid for phase fault protection. But earth fault protection of any line, for earth fault protection of any line, reactance relay is preferred. I hope this is clear. So for the present question, more relay is used for what? Long transmission line only. Yeah. I hope this is clear. So you can use any trick to remember the answers. Okay. These are the commonly asking question, Nana. Okay. I hope this is clear. We'll move on to the next question. The fault current is 2000 ampere, the relay setting is 50% and the CT ratio is 4000 by 5 ampere. Then flux setting multiplier will be, actually there is no units for flux setting multiplier. I don't know why he has given the units. So these are the questions I took from CL Wadhwa only. No units actually. Okay. So the formula for flux setting multiplier, if you notice, the flux setting multiplier formula is the fault current divided with CT ratio into current setting in amperes. See, what is current setting in amperes? Okay, current setting in amperes means current setting in percentage divided with 100 into I relay. If relay current rating, I relay means relay current rating. If it is not given, you take the secondary current rating of the CT. You have every right to take that. Secondary current rating of the CT is our reference. So current setting is given 50%, fault current is given 2000 amperes. So now let me write here the formula. So this is 50% by 100, which will give you 2.5 amperes. Now if you substitute back here, what I get? The fault current is what? 2000, CT ratio 400 by 5, then this is what? 2.5. Just check it what you get. So you will get an answer 10, I guess. So yes, straight away the answer is what? None of the above. Any doubts here? So we get 10,000 by 1000, that is what? 10. This is also very famous question, okay, from protection. So we'll move on to the next question. The ratio of reset to pickup current for an induction cup relay is, see, in case of induction cup type relays, basically we have two constructions. So again you need to remember this, what I am trying to say. We have electromagnetic attraction principle and induction principle. electromagnetic attraction principle. Electromagnetic attraction principle, we are not going to get good reset to pickup ratio. Okay, so reset means the current at which the reset will happen, the current at which pickup will happen. So reset by pickup, we say reset to pickup ratio. Otherwise you can write like this, reset to pickup, which is generally in between 0.6 to 0.9. And other question, for electromagnetic attraction principle, whatever the reset to pickup you are just written, reset to pickup, for because electromagnetic attraction principle works for both AC and what, DC. It works for AC and DC. So AC we can maintain a good reset to pickup ratio. Even this question also n number of times it is given. Remember this. See, reset to pickup for AC you can push up to what, 0.9 to 0.95. For DC, whatever you do, it is always 0.6 to 0.9. With special construction we can achieve this. For DC we can improve reset to pickup ratio, but AC you can't do anything. Sorry, AC we can improve, DC you can't do anything. Yeah. So yeah, the next important thing is that, what about for induction principle? Yeah. For induction principle, any construction you take it, I'll use another color pen. Yeah. Okay. For induction principle, any construction you take it, you name it any construction of induction principle. In induction principle, we have a different constructions like shaded pole structure, watt-hour meter structure, induction cup type construction. These are the basically three construction: induction cup type construction, induction disc type construction. Induction disc type construction, again shaded pole structure, we have a watt-hour meter structure. So for induction principle, the reset to pickup ratio, whatever I am writing, that reset by pickup will be very close to 1. So 0.95 to 1. This is what the information related to the question. Now you can answer. What is the answer for this? Now everybody can answer now, right? Okay, the answer is what? You're right. .99. I hope this is clear for you. Good. We'll move on to the next question. If the phase angle of the voltage coil of a directional relay is 50 degrees, the maximum torque angle of the relay is, again this is a question related to protection. So very simple, you need to understand like this to answer this question. See, voltage coil, yeah, let me show you one more thing here. Generally we connect a RC phase shifting network in series with the voltage coil. This R and C are what, variable. The main objective of this is to control the maximum torque angle, whatever he is asking in the question. So together I will say, I'd like to say, what is the voltage coil circuit impedance? The voltage coil circuit impedance is what? Mod ZV at an angle plus or minus theta V. You can make it plus and you can make it minus. That all depends on how you are adjusting this, because this will offer what? RL circuit, this will offer RC circuit. So okay, you can have a control over the, by adjusting R and C, you can have control over theta V and ZV also, but main intention is theta V. What is this voltage coil? Phase angle is given 50 degrees. So the phase angle is given 50 degrees, right? So from this I can conclude that theta V given in the question is 50 degrees. Now there is another thing, that theta V plus tau always equal to 90 degrees. Now this is called maximum torque angle, whatever he is saying in the question. So if this is 50 plus tau, that is equal to 90 degrees. Now what is this tau? 90 minus 50, which is what? I hope 40 degrees. So the answer is none of the above. Yes. Any doubts here? It's not 130. I hope this is clear for you. So we'll move on to the next question. All right. A reactance relay is what? Okay, again this is also a commonly asking question from the, the reactance relay, impedance relay and Moore relay. Actually the net torque equation of impedance relay is K1I square minus K2V square. So this is what impedance relay characteristic equation, net torque equation better to say. So here voltage is the restraining torque provider, current provides the operating torque, that's why, so it is a voltage restrained over current relay. But whereas reactance relay, the net torque equation is K1I square minus K3Vi cos of theta minus tau. Now we say this is called directional unit. Again this is current unit. Directional unit is providing the restraining torque, current unit is providing the operating torque. This is for what? Our reactance relay. Again Moore relay, it is basically a directional relay. This is Moore relay. Now by seeing this, what you can understand? Moore relay is called voltage restrained directional relay. Reactance relay is called directional restrained over current relay. Impedance relay is called voltage restrained over current relay. Current unit provides the operating torque, it is over current relay. Directional unit is providing the operating torque, it is a directional relay. In fact, Moore relay is a directional relay. These two are non-directional relays. Why? Because current positive or negative, operating torque is always positive. That means the relay cannot sense the direction of current. For both the current, operating torque is same. That means positive current you take it, negative current you take it, the operating torque is same. So yeah, present question, reactance relay. What is this? Now you can say it is a directional unit is providing the restraining torque. That's why it is a directional restrained over current relay, Mike. Yes, so it is a directional restrained over current relay. Yeah. See, this is the voltage unit, this is the current unit, and this is the directional unit. This is called operating torque. Positive, this, all these three operating torques, these are called restraining torques. Voltage unit, providing, here voltage is there in the restraining torque, providing the restraining torque. Current provides the operating torque kada. Current providing the operating torque means over current relay. This is called directional unit, because when current positive, this torque is positive, when current negative, this torque is negative. So that's why the point is clear. Okay, so directional unit is providing the operating torque, current unit is providing the, directional unit is providing the restraining torque, current unit is providing the operating torque. That's why it is called directional restrained over current relay. For directional relay, phase angle equal to theta max, so it is actually 50 degrees. So I don't know, Srinith, Mr. Srinith, that is conceptually wrong, Nana. For previous question, the voltage coil phase angle is theta V. Okay, no? So theta V plus tau always, tau is the maximum torque angle. Theta V plus tau always equal to 90 degrees. So maximum torque angle is 40 degrees. You just verify. Verify your concept. A shunt fault is characterized by, I am going to write the characteristics of shunt faults. Again, you can answer easily. Shunt fault means short circuit fault, first of all. What are its characteristics? Number one, there is a proof for each and everything, but I am not going to that discussion. Please remember, shunt fault characterized by increase in current. I will use the symbol, current increases, voltage decreases, impedance also decreases. That's why current increases. Okay, na? Next, power factor. PF means power factor. During fault, power factor decreases. During fault, you know, the angle between voltage and current, angle between V comma I, very close to 90 degrees. Temperature also increases. Why temperature increases? Current increases, I square R losses increases, temperature of the equipment increases. There is a slight decrease in frequency. Pressure inside the transformer tank increases. Pressure inside the transformer tank increases. In fact, these are all actuating quantities. Okay, na? Now tell me, increase in current, reduction in frequency and power factor is the correct answer. Power factor decreases. Yes or not? I hope this is clear for you. All right, we'll move on to the next question. The most economic load on overhead line is, see, for overhead lines, generally the economical loading is always greater than surge impedance loading. Let me write short form of overhead transmission lines, OHTL. Economical loading or practical loading. Economical loading, right? Or practical loading, which is always greater than surge impedance loading. Okay. For underground cables, if you notice, the economical loading is always less than what surge impedance loading. In case of overhead transmission line, the loading is generally limited by stability. In case of underground cable, loading is generally limited by thermal limit. Loading is always limited by thermal limit. Careful, this is also commonly asking question. The load carrying capacity of underground cable is limited by thermal limit. For long lines, for long overhead transmission lines, stability is the correct. But short lines, very short lines, you don't have a stability problems. In that case, the loadability is limited by thermal limits. Remember this. The loadability of long overhead transmission line is limited by stability limit. The loadability of short overhead transmission line is limited by thermal limit. But underground cable, there is no concept of stability problems. Always loadability is limited by thermal limit only. Yeah. Now the present question talks about economic load on overhead line is. Economic load on overhead line is always greater than what? Natural load. Surge impedance loading is also called natural loading. Don't confuse. Surge impedance loading is also called natural loading. Surge impedance loading is also called ideal loading. Ideal loading, natural loading, surge impedance loading, characteristic impedance loading, all are same. Okay, be careful about this. So always greater than the natural load. Okay, now. I hope this is clear for you. Chalo, we'll move on to the next part of the question. Sorry, next question. So any doubt? Yeah, for medium transmission lines, we generally say the loadability is always limited by voltage regulation limit. Medium transmission line, voltage regulation limit. Short line, thermal limit. Long lines, stability limit. But for underground cables, always it is thermal limit. This is also another kind of question you can expect. Okay, fine. Yeah, the next question. For long transmission line, for particular receiving end voltage, when sending end voltage is calculated, it is more than the actual value when calculated by. Actual value means what? Practical value. So generally, if you notice the formula for Vs, sending end voltage equal to what? Parameter A into Vr plus VIR. So for all the methods, VR and IR is what? This is what load data we say. VR and IR is same. Now you need to talk about A and B parameters. So for example, if it is a loaded capacitance method 1 plus YZ, this is loaded capacitance method. T method, A is what? 1 plus YZ by 2. Pi method also A is what? 1 plus YZ by 2. But what about B parameter? The parameter B is what here? Z. Let me write here. Yeah, parameter B is what here? Z. Here the parameter is what? T method Z into 1 plus YZ by 4. Here B is what? Z. See, Y into Z product is generally negative. Remember, Y into Z product is generally negative. So A is lowest for what? This method. A is lowest for what? Loaded capacitance method. Load end capacitor method, better. Load end capacitor method. A is the lowest one. So that will definitely give lowest sending end voltage. Forget about this. This is not the answer. Now in between T and pi you have to check. So since B is less here, B is more here, because B for pi model is greater than what? B for what? T model. Because A is same, T and pi. So that's why Vs is more for the nominal pi method than nominal T method. Okay, Vs we are talking. Vs equal to AVR plus BIR. A is lowest, 1 plus YZ. Don't see YZ is positive. If you think YZ is positive, you get the wrong answer. Option A is the correct one. But it's not the option A, it is the option C, believe me. Why? Any doubts here? So B is highest for what here? In between T and pi, B is highest for what? The nominal pi method. So that's why that contributes for more value of Vs. Okay. So the next one is the per unit impedance value of an alternator corresponding to base value 13.2 kV and 30 MVA is 0.2. The per unit value for the base values of 13.8 kV and 50 MVA will be. See, this is the new kV base. This is new kV base. This is new MVA base. This is old kV base and old MVA base. So there is a formula to calculate the new per unit reactance. We say X per unit new equal to. This is also a very famous question. X per unit old into KVB old by KVB new whole square into MVAB new by MVAB old. Okay. See what is X per unit old, which is 0.2. KVB old 13.2. KVB new 13.8. MVAB new 50. MVAB old is what? 30. Now check. If you do any mistake, you will get the answer wrongly. Careful. So better to substitute like this. It will not take much time. Okay. Very less chances to commit a mistake if you do like this. We get approximately 0.305. But option nearest answer is 0.306. Okay. Yeah. I hope this is clear, right? All right, sir. We'll move on to the next question. My suggestion is for this kind of question, this is a commonly asking question, because here KVB old, KVB new, and that square will be there, MVAB new, MVAB old. Don't do the calculations in air. Write down the formula. Do you think it takes minutes of time? No. It takes hardly 20 seconds. You know the formula, but if you do the calculations in air and if you do substitutions and if you calculate quickly, definitely there is a chance of ending up with wrong answers. My suggestion is write the formula, okay, and do it clearly. Okay, now please guys, okay, don't lose the marks for these simple questions. Okay. All right. Yeah, we'll move on to the next question. For stability and economic reasons, we operate the transmission line with a power angle in range. See, I'll tell you one thing. Frankly, when the generator is more stable until delta equal to 0 degrees. Simple way to say stability and reducing stability and instability. See, when the load angle close to 0, system is more stable. When the load angle is what? Close to 0, tends to 0, more stable. When the load angle is what? Close to 90, less stable. So by seeing this, delta 90 means almost system become unstable. Nana. Delta increases, na, stability decreases. Okay, now tell me. So this is one side regarding what stability we understand. Regarding economic reasons, what is the meaning of economic reasons? Economic reasons means you have to transfer more and more power from generator. See, if the generator, you set up the generator, if you install 1 megawatt thermal power plant, as per the today investment, it is approximately 10 CR, 1 megawatt. So you are invested so much of money by setting up thermal power plant, by setting up that generator has to deliver maximum power. When the generator will deliver the maximum power, because you know the formula P equal to P max sine delta, P equal to P max sine delta. When the generator will deliver the maximum power the generator can deliver if the load angle is what? 90 degrees. If load angle is what? Close to 0, power is what? Close to 0. If the load angle is what? Close to 90 degrees, power is what? Maximum. So delta 90 degrees economical, but system become what? Unstable. So we can take a best compromisation between these two. That is what? Around 45 degrees. That's why we never operate the machine more than 45, because okay, you may think that if I operate more than 45, fine. If you operate more than 45, power will increase, but the stability will decrease. That's not good. Clear? So that's why the best thing is always not greater than 45. So you generally it will be selected in the range of what? 30 to 45 degrees for stability reasons. Okay? Clear? Even there is another explanation, is that stability indicated with synchronizing power coefficient K, that is what? Dou P by dou delta. What is dou P by dou delta? P max cos delta. What about P? P max sine delta. If you plot these two curves, they are going to meet at what? 45 degrees. This is P curve, this is 90 degrees. At 45 degrees, both will meet. This is cos curve. So what is this? 45 degrees, you get what? At 45 degrees, what I get? At 45 degrees, P 0.707 times P max. Synchronizing power coefficient K, that also 0.707 times P max. So this indicates the stability, this indicates economics. So better you should not cross 45 because system become unstable. That's why the best answer is this. Have a look. Okay, so we'll move on to the next question now. Have a look of this. For lumped inductive load with increase in supply frequency, please answer this question. This is really a nice question. For lumped inductive load. Inductive load means what? Basically it is RL circuit. What I can write Z, the current is what now I, voltage is V, okay, Z equal to, we can write R plus JXL. I equal to V by Z. But what is power, complex power? S equal to V into I conjugate. So what I get now for a lumped inductive load? In this, real part is active power, imaginary part is reactive power. So V into V conjugate by Z conjugate. V into V conjugate is what? Magnitude only, V square. Let's say this is V bar, I bar. Better. So V square by Z conjugate means what? Magnitude of V square by R minus JXL. Okay. Now tell me what I can write here. I will multiply with R plus JXL and divide with R plus JXL. So I can write like this. R plus JXL in the numerator. In the denominator, what I get? R square plus what? XL square. Okay. R square plus XL square. So now tell me, P equal to, we can write if you compare the real and imaginary parts, directly I am writing. So little analysis is required. If the frequency increases, think about it. If the frequency increases, what happens? See, XL is directly depends on what? Frequency. Yeah, R is very small when compared to what? X. Yes, whenever there is a P frequency increases, tell me what I can write now. Frequency increases, R is very small, you can neglect this. Okay, so it is what? Inversely proportional to the F square approximately. And what about Q? Inversely proportional to what? F. Because if R is neglected in front of XL, Then what, XL by XL square. So both are inversely proportional to the frequency, I guess. So I can say P decrease and what, Q decrease if frequency increases. I hope this is clear, right? Yeah, we'll move on to the next question now. Yeah, oh sorry, this is P decrease and Q decrease. I'm very sorry. The option is D. Both decrease, na? Frequency increases. Yeah, P and Q both decrease. Answer is D. Yeah, you're right. Yeah. The supply voltage V in the diagram below. This is a network question actually. So you know this. This is purely real part. This is the impedance JXL. This is what, minus JXC. This is what, real voltage. These two are imaginary voltages. So that's why what is voltage V bar means we can write like this: 40 plus J70 minus J100 volts. Truly speaking. Okay. Having some angle overall this, because that depends on current angle. I am assuming that the current and voltage is what, in phase. Current angle I am assuming 0 if that is the case. This is the, so what I get now, 40 minus J30. Since magnitude of V under root of what, 40 square plus 30 square, so which is 50 ohms. Yeah. See, what is great here is I, right? What is this voltage? 40 volt equal to I into R, nana. What is this? 70 equal to JXL into I, na? XL into I given here, 70 volts. Okay, that way you need to see. Now 100 is given, na? What is that? Minus JXC into I. So what is that 100? This is 100. This is 70. This is 40 given. So plus J is there now. Okay, right. That's it. Just hold on. All right, we'll go to the next question now. Let's see this question. A three-phase breaker is rated at 2000 MVA 33 kV. Its making current will be. See how to calculate the making current. See, by default, this is what symmetrical breaking capacity. This is what the rated voltage. The symmetrical breaking capacity equal to root 3 times VL into ISY. ISY is the symmetrical breaking current. The making current IMC for a circuit breaker is, these are the formulas, 2.55 times the symmetrical breaking current. This is standard formula. By using this, first you calculate the symmetrical breaking current, then you can calculate the making current. So 2000 MVA, 2000 into 10 power 6 kada, root 3 into VL, 33 into 10 power 3 line voltage, symmetrical current ISY. What is this ISY? You can calculate in kiloampere better. So 2000 divided with 33 divided with root 3. So this is approximately 35 kiloampere symmetrical breaking current. You multiply that with 2.55. We get 89.22 kiloampere. Making current is so the nearest option is what? D. Okay, nothing great about this question. I hope this is clear for you. Okay, next question. The phase modifiers is normally installed in the case of, what is phase modifier? Basically, it is called synchronous phase modifier. Synchronous phase modifiers. It is a synchronous motor. It is basically a synchronous motor. Nothing but synchronous motor. Let me write synchronous motor, but operating under no load. It is a synchronous motor operating under no load. So it can be over excited and it can be what? Under excited. So but both over excitation and under excitation. Over excitation means what? It will inject the reactive power so that it will boost the voltage. Under excited means what? It consumes the reactive power and it will buck the voltage. So this kind of operation is generally required for long lines, because for short and medium lines there is no need of, no need to buck the voltage, because there is no concept of Ferranti effect. Ferranti effect, if you ask me, generally coming for what? Long lines. You don't have a Ferranti effect for medium and what? Short lines. So for long lines onwards we have a possible Ferranti effect. So that's why, yes, to buck the voltage and boost the voltage, both operations it can be doing, because it will be over excited, it will be under excited. Over excited means inject the reactive power, voltage boost. Under excited means buck the consumes the reactive power, voltage buck. So that's why basically it is used for what? Long lines only, and it is what? Costlier. So better to go for what? Long lines. The voltage of a particular bus can be controlled by the controlling of, just now I discussed. you can control the reactive power so that you can control the voltage of any particular bus. Reactive power control will control the voltage of the bus. Yes or not? Clear? So if you want to control the voltage at any particular bus, you need to control the voltage at that bus. At any particular bus, you are injecting the reactive power. Just imagine. Then the voltage magnitude at that bus will increase. At any particular bus, if you are consuming the reactive power, at any particular bus, you are consuming the reactive power or you are drawing the reactive power. So voltage at that bus will what? Definitely decrease. I hope this is clear for you. All right. Okay, fine. We'll move on to the next question now. If alpha is the angle of the voltage wave at which an RL circuit is switched in and theta is the impedance angle of the RL circuit, there will be no transient when the circuit is switched in if, see, by default we take the sine excitation. So the voltage V of t is what? Vm sine omega t. Then the current drawn by RL circuit, if you notice, there exists a DC component and sinusoidal steady state component. So we are not worried about the, the sinusoidal component. The DC component introduce what? Transients. Now the DC component we get like this, plus alpha, right? Alpha is the point at which it is switched on. Okay. The DC component, we have a formula like this, Vm by mod z sine of alpha minus theta e power minus t by tau, where tau is the time constant of the circuit. So when the the DC component 0, DC component 0 means no transients in the circuit. 0 indicates what? Okay, let me write here. If this is 0, no transients in the circuit. This is not the complete current. There is a DC current and steady state sinusoidal current. I am not taking into consideration of that. So now tell me, what is the answer? There will be no transient in the circuit when it is switched on. Sine of alpha minus theta is 0. Alpha minus theta is 0. Alpha equal to theta is the answer. So I feel the best answer for this question is A. But again, that depends on the excitation. Sometimes he will give you it is a cos excitation. Cos excitation answer is different. Sine excitation is answer is different. So that's why it has to be mentioned the excitation, but generally we take what? Sinusoidal excitation. Okay, sine excitation. So alpha equal to theta is the answer. Cos excitation, yes, you're right. Here cos of alpha minus theta, that will be 90. So alpha equal to 90 plus theta, you get it. So this is an ambiguity question, I can say. Yes. Is this clear, everybody? Now we'll move on to the next question. So the connected load of a consumer is 2 kilowatt and his demand factor is and its maximum demand is 1.5 kilowatt. The load factor of the consumer is, okay, the point is here, is it possible to calculate the load factor using this data? Actually, we can calculate only demand factor but not load factor. Okay, let me tell you. What is the connected load? 1.5 kilowatt. Demand factor formula is connected load by maximum demand. Sorry. That you can calculate. But load factor is what? Average demand by maximum demand. So from the data, it is impossible to calculate the average demand, the connected load given. So if the question is demand factor, the answer is what? 0.75. Now what is the average demand? Unknown. Then maximum demand is what? 2 kilowatt. Sorry, 1.5 kilowatt. So by this question, I will suggest you to go for what? D. Why? He has not mentioned, the average demand. From the given data, it is not possible to calculate. I hope this is clear. Okay. This is the next question. Have a look of this. The leakage reactance of a 50-kilometer long cable is 1 mega ohm. For 100-kilometer long cable, it will be. See how to calculate this. It's very simple. The leakage resistance, right? Leakage resistance or insulation resistance, or insulation or leakage is same. Generally, this is the terms related to capacitance or cable or leakage or insulators, which is inversely proportional to the length of the line. If length increases, this insulation resistance or leakage resistance will what? Decrease. So length is doubled and this become off. So I can write like this: R1 by R2, L2 by L1. R1 is what? 1 mega ohm. Okay, so that implies R2 is, but you don't have an option, so answer is D. Oh, I'm sorry. Yeah. Is this clear, everybody? I hope this is clear for you. All right. We'll move on to the next question. The coefficient of reflection for current and open-ended line is, actually, let me tell you the formulas for coefficient of reflection for voltage, coefficient of reflection for current. Okay, maybe I'm using this symbol, coefficient of reflection for current, Zs minus Zl by Zl plus Zs. Coefficient of reflection for voltage is what? Negative to this, exactly negative. ZL indicate load impedance, Zs indicates, the surge impedance of the line. See, this is the line where it is terminated with an impedance called ZL. The surge impedance of the line is Zs. There will be a reflection here. Okay. Now tell me, for this, you take ZL common. C dash I So what I get now? ZL get cancelled. ZL tends to infinity means this is 0. 0 minus 1 by 0 plus 1. Option is C. Okay. The inductance and capacitance of a system is given, and the instantaneous value of current is interrupted is 10 ampere. The voltage across the breaker is, whenever the instantaneous value of the voltage here you want to calculate across the breaker when the current interrupted is I, this is actually a current chopping phenomena. V equal to I into root over L by C. I is given 10 root over L 1 Henry by let's calculate this. These many volts. We get something like 0.01, that is what, 100 into 10 power 6. 100 you take it out of this volts. 100 kV is the answer. This is a question related to what? Circuit breakers. Clear? Any doubts? We'll move on to the next question. Okay, next question we'll see now. The capacitance inductance per unit length of a line is given. The surge impedance loading of the line is, okay. Surge impedance loading means what? The rated voltage square. Surge impedance loading means rated voltage square or line voltage square divided with what? Surge impedance. The formula for surge impedance is root over L by C. L given 2 millihenry, C given 0.01 microfarad. So what is the answer you get? We get 447.21. (27 megawatt). So the surge impedance loading, this is K square, no? We get by default mega. Actually, it should be megawatt. I don't know why it is given. Better it should be what? Not MVA, megawatt. Okay, so you get 27 megawatt approximately. So the answer is what? C. I hope this is clear for you. Okay. So let's try this question, everybody. An alternator is delivering balanced load at a unity power factor. The phase angle between line voltage and line current is. What is the answer? Okay, let me check the options. It's a nice question, interesting question. Many D, some people got fine. D is a trap, amma. D, option D is the trap. See, okay, what the people will see here? They will see simply what? Okay, wait. Yeah. What they will see is unity power factor. Unity power factor means the angle between V phase and I phase is what? 0. But what is asking? The angle between line voltage and line current. But if you want to answer this, you should know the first thing, whether the generator is star connected or delta connected. By default, the generator is star connected. Star connected, line current equal to phase current. But line voltage equal to root 3 times phase voltage angle plus 30. So now tell me, what about the line current angle? Same as phase current angle, but the line voltage angle is what? Plus 30 degrees. Compare it to phase voltage angle. Right or not? Clear? Angle between V phase and I phase is what? 0. Fine. You may also say like this, theta V, voltage angle minus what? Current angle is what? 0. But now angle between line voltage, line current is what? Line voltage angle is what? Phase voltage angle plus 30 minus current angle, line current angle, phase current angle is same, theta I. So what do you get now? Theta V minus theta I is 0 plus 30. So the answer is what? 30. $90 plus delta meaningless nana. 90 plus delta అనేది meaningless. ఓకేనా? Okay, next question. A system is said to be effectively grounded. What is the meaning of effectively grounded? Effectively grounded means what? Solidly grounded. Neutral reactance is very small, 0. Actually, zero sequence reactance is what? The original zero sequence reactance of the generator plus what? 3xn. So that's why if you see the ratio between x0 by x1, that is greater than 3, which is called what? Reactance grounded system. Reactance grounded antam manam. If x0 by x1 is less than 3, then it is called what? Effectively grounded system. For effectively grounded system, x0 is what? Less. Okay. So the best answer is what? Because xn 0 na, xn equal to xg naught, xg naught is very small. Okay, so we'll take a short break here for 15 minutes. I'm not going to end up this live session. Till here we finished 25 questions as of now. So let's take a 15 minutes break. After the break, we'll continue for the remaining questions. I hope this is clear for you. After the break, we are going to see some very interesting questions. Most of the questions related to T&D and other topics. Okay. Yeah, less than 3 means what? Answer is D, correct. All right, I will be back in 15 minutes. Now it's time almost 8:40. Yeah, 8:55 we'll meet. Okay. So yeah, these kind of questions, yes, we can expect in the final exam. I never say the paper will be very tough. Paper will be moderate. It's a mix up of what? Numerical question and what? You know, some theory kind of question. Okay. So, but at this stage, you should be very confident regarding the exam. And I would like to say one thing. Many people are even attempted some, you know, the test series, like especially full length mock test. So the people who attended full length mock test, even though they went with good preparation, they may be end up with what? Less marks in full length mock test. It happens because that generally we try to give somewhat tough questions in the, you know, the in the mock exam sometimes. So maybe because of that, maybe the time constraint and everything really matters. That's why you fail to score good marks in the exam, in the mock exam. But don't think that what it is your final exam, it's your final marks. Don't disappoint by seeing that. Okay, at this stage, stay focused, you know stay confident, okay, without any disappointment. Is very, very important at this stage of preparation. Be happy with the preparation what you have done till now, okay, because the result is never be in your hand. You can't change it, you can't create it. The only thing is what you act as per the situation in the paper. So when you face the final paper, maybe it might be tough or it might be easy, or it might be very, 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 very simple paper, but still, okay, confidently you attempt every question. Read the question very carefully. Generally, we people will fail by reading the question, by understanding the question. Okay, we sometimes tempt by seeing the question. The questions will be sometimes very tempting to attract the wrong answer. So you please try to avoid these things, so and things become very simple at the end. Okay, be happy with your preparation, because in the next 5 to 10 days, don't touch the new things much. If it is a very small things, okay, you can go ahead, but it's not like complete subject you are, for example, till now maybe one subject you are not at all studied. Don't touch it, as per my point of view, because still you have just matter of what 1 week. So that's why, so be careful. Okay, few things you prepare, but not like all the new subjects. If you want to study now, means it's not possible. Whatever the preparation you have done till now, fine, happy with that. Go ahead with the exam with positive mindset and the confident mindset. Definitely it will give you a boost. Okay, anyway, so now it's 8:40. Okay, we'll meet at 9 p.m. now. Okay, no? So I'll stop here for short break. Thank you. All right. So we'll start the session now. We'll move on to the next question. I hope my voice is clear, right? All right. Okay, so I can do 100 plus questions, Mr. Sunil Kumar, but the time is not sufficient for us. Okay, so if possible, I will conduct one more session also, not a problem. Don't worry. Okay. So, all right, we'll move on to the next set of questions. Yeah, the insulating materials with breakdown strength of 250 kV per centimeter, 200 kV per centimeters, 150 kV per centimeters, and their permittivity is 2.5, 3 and 3.5 are used in a single core cable. If the factor of safety of the for the materials is 5, that means all the materials having same factor of safety. The location of the materials with respect to the core of the cable will be, core of the cable means conductor. Yeah, I can do it, don't worry. So, with respect to what, different materials you see, the material which is having highest product of epsilon r g by f placed immediately after the conductor. This is the criteria for that. Where F1, F2, F3 are factor of safety of these three materials. See, this is the logic we need to follow. Okay. The material which is having highest product of epsilon into G product by F1, F2, F3. F1, F2, F3 is same for all the materials. So that's why you must see what epsilon R1, G1 should be greater than what? So let's multiply that. So he is talking about epsilon R. First material of epsilon R is what? 2.5, which has 250 into what? 2.5 is the product. Let me write somewhere here. 2.5 material is what? 2.5 into 250. Second material is what? Epsilon R is 3. 3 into 200. Epsilon R is 3.5. 3.5 into 150. Let's calculate them. 2.5 into 250 will give you 625 here. This is 600. 3.5 into 150, 525. So the order is what? Same. 2.5 is the first one, then 3, then what? 3.5. Starting from core. 2.5, 3, 3.5. I hope this is clear, right? All right. We'll move on to the next question. The sending end voltage of a feeder with reactance 0.2 per unit is 1.2 per unit. Okay. So that means what is given here? There is a feeder whose sending end voltage is 1.2 per unit. Its reactance is what? 0.2 per unit. The receiving end voltage is not given. If the reactive power supplied at the receiving end of the feeder is 0.3 here, QR is 0.3. The approximate voltage drop of the line is, what is the formula for QR? Vs by Ex into this is the formula. But since active power is not given, you can take approximately 0 means delta 0 cos 0 1. So approximate formula is Vs by X So there is a small correction in the question. Just hold on. This is VR by X. Yes, this is correct now. But the question is here VR is not given. So approximate voltage drop in the feeder is, this is not at the receiving end. If it is sending end, then only we can solve. Otherwise it is not possible. Okay. See, if it is sending end power, then what is the formula? Vs by X minus, so cos delta is approximately 1, so Vs minus Vr. Now tell me, this is what sending end, then only we can solve, otherwise not possible. This is what the voltage drop. What is Qs? What is X? So the answer is okay. I hope this is clear for you. So sending end reactive power formula is what? Vs square by X receiving end reactive power formula. These are the formulas. Okay, so we'll move on to the next question. If a synchronous machine is overexcited It takes lagging wires from the system when it is operated as. See, first of all, question itself is wrong. If synchronous machine is overexcited, then it takes lagging wires from the system when it is operated as a. It may be generator or motor. If it is overexcited means it supplies the reactive power. Supplying of reactive power means supplying of lagging wires. Consumption of leading wires. This is true from what? It may be generator and what? Motor. When you are supplying reactive power means supplying of lagging wires, consuming of what? Leading wires. So what is thou? This is what? Overexcited case. Underexcited case, reverse. It consumes the reactive power, consumes the lagging wire, supplies the leading wires. So the option is none of the above. Based on overexcited or underexcited, we never say it is a motor or generator. It will draw reactive power. When it is overexcited means supplies the reactive power. Taking of lagging wire means consuming of reactive power. That is not happened for synchronous machine, no matter whether it is generator or motor. The question itself is wrong. That's why the best answer is none of the above. Here, next question. If IA1 is the positive sequence current of an alternator and Z1, Z2, Z0 are the sequence impedances of the alternator, the voltage drop produced by the current IA1 will be. It's very simple to answer this question. See, if the network is balanced for a synchronous machine, it is a balanced machine. Means what? Having same impedances in all phases. Whenever the machine having same impedances in all phases, the sequence impedance matrix is a diagonal matrix. So the voltage drop produced by the positive sequence current is what? Always IA1 into Z1. Voltage drop produced by the negative sequence current is IA2 into Z2. Voltage drop produced by the zero sequence current is IA0 into Z0. The voltage drop always depends on what? The respective sequence current. Okay. The option is what? A. This is called positive sequence voltage drop, negative sequence voltage drop, zero sequence voltage drop. Clear? I hope this is clear for you. Now, let's see. For the system shown below, if there is a line to ground fault on the line side of the transformer is equivalent to, is a delta star grounded transformer. One can easily understand that. For a delta star grounded transformer, let's see. Let's see if there is a LG fault on one phase. Small a, small b, small c. If there is LG fault, now here is the fault current I. This current 0, this current is what 0. So the corresponding winding, this there is a current here I. If that is the case, IA is what I. IB equal to what? Minus I. What is this current? 0. What is this current? Also 0. Why? There is no current in B and C phases. If there is a current in A phase, there is a current in AB phase here. If there is a current in B phase, there is a current in BC phase. If there is a current in C phase here, there is a current in CA phase. So IA, IB is there. Now IC is what? 0. By seeing this, what you can understand? It is a phase to B phase fault, LL fault. So line to line fault on the generator side of the transformer. LG fault equivalent to LL fault. LL fault equivalent to 3-phase fault. Okay. I hope this is clear for you. Yeah, if the inductance and capacitance of the system is given, so I think the same question, no, the value of the shunt resistance across the breaker for critical damping is, for critical damping, this is called resistance switching. There is a resistance connected across the circuit breaker. This is a resistance switching commonly employed for air blast circuit breaker. To reduce the current chopping and restriking voltage, we do this resistance switching concept. The value of resistance to be connected across the circuit breaker contact is 1 by 2 under root L by C. L is given 1 Henry. So what I get now? 100 into 10 power 3. So we get what? 10 into 10 power 3. So 10 kilo ohms by 2, which is what? 5 kilo ohms. Okay. Now we'll move on to the next part of the question. Okay, we'll move on to the next question now. A 100 by 5 current transformer has a secondary winding and lead resistance is 0.2 ohms and the secondary burden is 5 volt ampere. The V output is. Just try to solve this question. Okay. So indirectly, at what current it is solved? The secondary burden, the relay burden, which depends on what? The pickup current. So total resistance equal to 5. Okay. Yeah. I square into R. So what is a pickup current? Just answer this. 25 root, which is 5. So exactly at pickup current 5 ampere, you got the, the relay burden. The secondary burden is what? 5 volt ampere. What is VA output? How to calculate the VA output? So the VA output always depends on the pickup current and the secondary voltage. But what pickup current it is calculated? The VA output, no? There is a small correction here. Just hold on. The lead resistance also given, no? Secondary winding and lead resistance together given. By default pickup current is 5. It has to be mentioned the VA output of relay or something. Okay. 5 ampere is flowing through the lead resistance. Okay. So I'm going to answer this question later. The VA output has to be mentioned. So VA output means what? Should be the relay burden actually. It's not the secondary burden. If it is given relay burden only, it will be correct. Okay. Yeah, I will going to answer this later. Don't worry. So relay burden means relay burden is different and VA output is different. See, generally VA output means what? That is a CT VA output if it is considered like that. Relay burden plus what? Lead. Power consumption at lead. CT VA output. If that is the case, we get 5 VA. Suppose if you want to calculate relay output, relay VA output, for example, then CT VA output minus what? Power consumption in lead resistance. It's given secondary winding and lead resistance. Okay. Okay, anyway, I'm going to answer this later, don't worry. Yeah, a single line to ground fault occurs on an unloaded generator in phase A. If xg equal to x2 equal to 0.25 per unit and x0 is 0.15 per unit, the reactance connected in the neutral xn is 0.05. The initial pre-fault voltage is given. The magnitude of the fault current will be, for LG fault, what is the magnitude of the fault current? The fault current for LG fault is what? 3 into E by. The only twist is here whether this x1 is given or not. xd is nothing but what? X1 only. Okay, x1 is given 0.25. Pre-fault voltage is given 1. 0.25 plus 0.25 plus xg not given 0.15. Neutral given what? 0.105 means 3 into 0.05. This gives you the magnitude of the fault current for LG fault. So 0.25, 0.5, 0.15, 0.8, 0.125 we get. 1 by 0.8 means what? 1.25, 1.25 into 3. 3.75 per unit. Okay. Just hold on. I hope you can able to see. More relay, plane impedance relay, directional relay, angle impedance relay. See, this is more relay means circle passing through the origin. This is called angle impedance relay. Always some inclined line. Straight line passing through the origin is nothing but what? Directional relay. Circle center at origin is nothing but what? Impedance relay. Plane impedance relay. So please remember these characteristics, which is very important. I hope this is clear. Yeah, A4, B1, C2 D3. Yes, you are right. So we'll move on to the next question. Yeah. So there is a star delta transformer with star side is grounded. Then the zero sequence currents. This is grounded, no? Another side delta. For a delta connection, the line value of zero sequence is always 0. But since there is a path here, there exists a line current here. The same current will go here, phase current. Okay. Similarly here. Line current and phase currents are same. Now there exists a phase current here, there exists a phase current here. Yes, this is what. So there exists a line and phase currents in star side, but delta side only phase current, no line current. Exist in the lines on both star and delta side, no. Has no path to ground, no. There is a path. Exist in the lines on the delta side, no. Exist on the lines on star side, yes, this is correct. This is the only best answer as per the given question. The zero sequence, line value of zero sequence current for delta connection is always 0. Okay, we'll move on to the next question. The connection diagram of sequence networks appear for a particular fault on power system. If you notice here, all the sequence networks are connected in parallel because positive terminal of what? Zero sequence, positive sequence, negative sequence are connected together, and negative terminal also connected together. Yes or not? Means three sequence networks are connected in parallel means it is a double line to ground fault. If all the three sequence networks connected in series, something like series means like this. What is this? LG fault. Only positive and negative sequence networks are connected in parallel means that is what? LL fault. Positive and negative are connected in parallel, LL fault. Only positive sequence network, there is short at its terminal, positive. This is for three phase fault. Yeah, all these three sequence, positive. This is called series connection. Current is same. Positive and negative sequence are what now? Parallel here. Yes, three-phase fault only, positive sequence network exists. Next, we'll see the another question. The inertia constant of a 100 MVA 11 kV water wheel generator is 4. The energy stored in the rotor of the synchronous generator at synchronous speed is. So at synchronous speed, kinetic energy is what? MVA rating into inertia constant. G is the MVA rating, H is the inertia constant. 100 into 4, right? So which gives you 400 megajoules. All are in parallel. There is no concept of anti-parallel. Okay, we'll move on to the next question now. A large AC generator is supplying power to infinite bus has a sudden short circuit occurring at its terminal. Assuming that the prime mover input and the voltage behind the transient reactance to remain constant immediately after the fault, the acceleration of the generator is, see the acceleration alpha, which is what? Accelerating power by m, where m is the momentum here, inversely proportional to the moment of inertia. Momentum J is the moment of inertia, H, they are what? All directly proportional. You may say alpha is inversely proportional to the momentum. Alpha is inversely proportional to the moment of inertia. Alpha is inversely proportional to inertia constant. Always same. So it is inversely proportional to the moment of inertia of the machine. That's correct. Okay. I will move on to the next question. The set of three equal resistance Rx connected in star across RYB terminal in place of load shown below. The unbalanced delta connected load, the value of Rx is. That means both will consume. That means all are what? Rx here. What is power consumption here? 3 into V phase square by what? Rx. Otherwise, V line square by Rx. But what about here? Only power will be consumed by this resistance. These two will not consume any active power. So what is power consumption here? Only one phase. What is that? What is the voltage across this? V phase square by what? 100. That is equal to V line square by 100. Why? V phase equal to V line. So now you just compare them. These two are what? Equal. Means what? So Rx equal to 100 only. The answer is B. V phase equal to V line for delta. Here it is 3 into V phase square by Rx. V phase equal to what? V line by root 3. So root 3 square means 3 get cancelled. Here in this 2 there is no power, active power consumption here. That's why simple way. Have a look. Okay, let's see the another question. The bus admittance matrix of the network shown below is marked parameters are per unit impedances. Actually, impedance is marked here. That's clearly mentioned. So that means bus 1 to ground, there is an impedance 0.1. Admittance is what? 10. Bus 1 to 2, the impedance is 0.2. That means admittance is what? Inverse of that, 5. So tell me, what is y11? Sum of the admittances connected here, 15. What is y12? Negative of the admittance between 1 and 2, minus 5 is also minus 5. Y22 will be what? Plus 5. 15 minus 5 minus 5, 5. Diagonal entries, the rule is sum of the admittances connected. These are impedances. If I inverse this, then only I will get admittance. Okay, clear. So what is off diagonal entry means? The negative of admittance connected between what? Bus 1 and 2. Now, let's see this question. The incremental fuel cost of the generating units are given. So total demand is 250 megawatt. Neglecting the losses, what is PG1 and PG2 is asking. Simple way to write is this P1 plus P2 is what? 250. This is one equation. The other equation is what? IC1 equal to IC2. If you want to get the minimum fuel cost solution, incremental cost must be equal. So if you write IC1 equal to IC2, what I get? 0.2 P1 minus 0.2 P2 equal to 32 minus 25, which is 7. Yes. So P1 minus P2 is the another equation. That is what? 7 by 0.2, 70 by 2, that means 35. If you write 1 plus 2, 2P1 equal to 285. So P1 equal to what? What is the answer? Tell me. What is the P1 you get? Think about 285 by 32 minus 75 is 2, then 285 divided with 2. 142.5. Actual answer is what? P1 is 142.5. P2 is what in that case? 107.5. That option is not there. But these are the original answers. Check it. Okay. So that option is not there. So nearest answer is what? This A. A is the nearest answer. Yes or not? Just check it. Now we'll move on to the next question. A single phase transmission line has an impedance of J.8 ohms, supplies a resistive load of 500 ampere at 300 volts. The sending end power factor is very simple to answer this question. See, it's supplying a purely resistive loads 500 amperes at 300 volts. In between, this is a sending end current, this is a receiving end current, both are same. But sending end voltage you need to find out. The receiving end voltage and receiving end current are in phase. What about sending end voltage? Receiving end current, let me write 500 angle 0 degrees. Why? Because supplying purely resistive load. What about the receiving end voltage? You take it reference 300 angle what 0 degrees. What about the sending end voltage? VR plus J.8 into IR. Because the impedance of the line is what? J.8. VR 300 ohms. IR 500. $300 plus J400. VR is 300. This is what VS. VS magnitude is under root of 300 square plus 400 square, it is 500. Now this is what the angle. VS and VR are in phase. Now what is this angle? Is nothing but what? Power factor angle. Now you know this length, VR length is 300. Now what is this angle? Otherwise cos theta. Cos theta equal to what? 500 cos theta equal to 300. Let me write like this. Yes or not? 500 cos theta equal to 300. Now cos theta equal to what? 300 by 500, which is what? 0.6. Lag or lead? Lag. VS lags the what? IR equal to what now? IS. So yes or not? VS cos theta is nothing but what? VR. What is the magnitude of VS? Tell me. 300 square plus 400 square, 500. So 500 cos theta equal to 300. The theta is the sending end power factor angle. Cos theta is the sending end power factor, which is 0.6 lag. Why lag means this IR or IS lags the VS. Okay. 0.6 lagging. So we'll move on to the next question. In a power system with negligible resistance, fault current at a point is 8 per unit. The series reactance to be connected to the fault to limit the short circuit current 5 per unit is very simple. When you connect a series reactance, the short circuit current will decrease. So what is the fault current after connection of reactance? V is 1 per unit by X plus what? That X external. Before connection of this, it is what? IF dash is this. Initially IF is what? V by X. IF is given 8. V is 1. X we can calculate. What is X now? 1 by 8, which is 0.125. Now what is IF dash, which is 5? That is equal to V is 1. X is what? 0.125 plus X external we need to calculate. 0.2. 1 by 5, 0.2. 0.2 minus 0.125, which is 0.075. The answer is what? D. Check it. Any doubts you have? In the solution of load flow equation, Newton-Raphson method is superior to Gauss-Seidel method because why Newton-Raphson method is superior to Gauss-Seidel method? See, time taken to perform one iteration in Newton-Raphson method is less. No, actually, one iteration time in Newton-Raphson method is more because you need to calculate Jacobian and its inverse. Whereas in Gauss-Seidel method, in one iteration, you are just solving simple algebraic equation. It takes very less method. So that's why this statement is wrong. Number of iteration required in the Newton-Raphson method is more when compared to that in the GS method. No. Number of iterations just 5 to 6, but Gauss-Seidel method will take huge number of iterations. Number of iterations required is not independent on the size of the system in the NR method. Number of iterations required is not independent on the size of the system. Yes, this is also a correct statement. In case of NR method, number of iterations is not depends on the size, but in case of GS method, it is depends. Convergence characteristics of the NR method are not affected by the selection of slack bus. This is also true, but I can say why Newton-Raphson method is what? Superior when compared to the Gauss-Seidel method means that is just because of what? You know, number of iteration required is not independent. Wait, not independent means what? It dependent, right? No, independent on the size of the system. This is also wrong statement. So only the option is what? D. That's it. When a 50 MVA 11 kV 3-phase generator is subjected to a 3-phase fault, the fault current is minus J5 per unit. When it is subjected to line fault, the positive sequence current is minus J4 per unit. Then he is asking what is the positive and negative sequence impedance. 3-phase fault, what is fault current means? E by X1. What is fault current? E by Jx1 better. IF is minus J5. E is what? So if I inverse this 1 by J 0.2, so X1 is what? 0.2 per unit. The positive and negative sequence. X1 0.2. Now LL fault will give you positive sequence current E by X1 plus X2. Okay, J will be there. IA1 is given minus J4. E is what? 1. J times X1 is what? 0.2. X2 we don't know. If I inverse this 0.25 you get, right? 1 by 4 is 0.25. If you compare X2 will be 0.05. So 0.2 and 0.05 is the answer. Point 0.2 and 0.05. Just check it your answer. Okay. 0.2 and 0.05. Check your answer. Line to line fault, the positive sequence current IA1 E by x1 plus x2. So answer is 0.2 and 0.05. 0.25 inverse only minus J4. Yes or not? If I inverse the 0.25, what is the answer? 4. Okay, so that's it. So with this, I'm concluding the session. All right. Yeah. With this, I'm concluding the session. So thank you and all the best for your preparation. All right. If possible, I will take one more session. But be confident on your preparation. Go with positive mindset. So all the best, guys. Thank you.